Alrighty, welcome to a sandals tutorial. Uh, this is pretty much being only made for one person, and sorry, there is my air conditioner in the background, and I do not have a proper microphone. This is certainly not studio quality. It will also not be edited or anything of that nature. It is just one quick go to get the ideas of how to work with the UI and how to build a creature and what the different nodes and connections do. That's its sole purpose. Quality is very second nature here. So sorry about that, but it'll get its job done. Alright, so over here we're running a simulation. I've been running this all night. And we can see we have 1,285 generations. And the creatures were able to go a whopping maximum, and I think the best score in generation is bugged out. It seems to be using the best score ever. But they went for a maximum trip of about 50 meters, which is awesome. Let's go take a look here. Actually, they're about to reset. Let's change that real quick. So we can see this is the worms and how they move. Look at them. Look at him go. He is trying his best to move forward. As is this guy. Good job, guys. Good job. So how did we get to this point? Well, first up, we created a worm. Second up, we let it run, and the evolver, named here the gene pool, did its job, and that was our result. So let's go through the gene pool real quick. Gene pool is very cool. What it does is, after a set amount of time, all the creatures here, they are killed, which we can see right here as that timer runs down. They are killed. They are added to the gene pool. Well, you can see that guy did real good. He got second spot. The gene pool then selects for them and puts them back into the simulation. So, when the gene pool selects for them, actually, we can see it culling 50% here. So what it does is it takes their score, normalizes it to the rest of the population, takes that number, which we can see here. So this guy's score was 39.85. Its normalized score, whatever that was squared, and that gave it 0.57. So you can see the top here is 1, the bottom here is close to 0, and then it takes that normalized score squared, multiplies it by 64, and then adds it to the gene pool that amount of times. So you can see here, that guy got 64 slots in the gene pool, and this guy, all these guys down here, only got 1. These guys here have 29, 30, 31, 33, 5, 41, 42, 8, 54, 64. And we can see that easily by the color grading. So instead of showing 54 of these creatures when they're all the same, he just has 54 slots in the gene pool, we just use a red to green color grading. So the gene pool will randomly select these guys, and keep in mind it's not selecting based randomly off of 1 out of the 256 slots here. It's selecting 1 out of the amount of creatures in the gene pool. So there's 64 plus 54 plus 48 plus 46 plus 43 plus 42 and so on. That's the actual number in the gene pool. So this number is probably close to a couple thousand. So they get spawned, they move forward, they die, their score is squared, they are selected based upon their score, and put back into the gene pool. Keeping in mind also that once the gene pool is full, 50% of the creatures will be murdered. Because we don't need, half a population of genetic stock. That is really crappy. I call that an extinction event, which is kind of like a real-life extinction event. If you can't survive a meteor hitting you, or oxygen levels plummeting, or in this case, just not moving forward very well, you will kind of go extinct. That's kind of the idea there. Alright, so that's the gene pool. And then over here we have the actual neural network editor. So let's pop into the editor. And over here we have a bunch of different options. Add, remove, move, collagen, muscle, muscle fiber, neural tissue, nerve, bone, select A group, select B group, connect A to B, push layer, a bunch of different nodes, clear and simulate. So clear is pretty straightforward. It will literally just clear the creature. Dut, 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 dut. Cancel that because I like my worms. Let's start with the connections. Alright, so each body here, except for the neural tissue, has a spring. I actually can't pop back into here now, otherwise I will erase the creatures, and now they are kind of stuck at, I think, 200 for their cycle, so, oh, what the heck. Let's reset this. It ran long enough. Everybody dies. Alright, simulation has been reset. Let's pop into the editor and simulate. Alright, generation lifetime, let's set that to the maximum, which gives us plenty of time to look at them. So each one of these here, except for neural tissue, has a spring. So when you see a connection, that is just a regular physics body spring. So back into the editor, we have springs and nodes, known as connections and nodes. So collagen is just your run-of-the-mill spring. That's literally all it does. Muscle is just a spring. However, based on the input signal that it gets at its start point, if it receives a signal of 1, it will try to contract 20 or expand 25%. If it receives a signal of -1, it will try to contract 25%. And that is pretty much all how a muscle or a muscle fiber work. So can't really see it here. So if we go into the simulate and reset that real quick, ignore that error. That happens sometimes. It doesn't seem to cause problems, and it will be removed eventually. Editor, let's simulate again, just to account for that bug. And the time runs down. They go to the gene pool. Let's zoom out, which will make that go faster. And there we go. Oh, and turn that back up so we can see. Alright, there we are. So we can see, especially in his tail right here, the muscles are expanding and contracting. Huzzah! So what's the difference between a muscle and a muscle fiber? Well, all of these guys here are muscle fibers, and that is so that they can pass their signal forward along. So the signal will go from here to here to here to here to here to here through the muscle fiber. A muscle does not have that ability. A muscle will simply contract or expand, and that is it. The endpoint will not receive the signal. So here, the signal will go through the muscle, through the muscle, through the muscle, through the muscle. There are muscle fibers. And here, with a regular muscle, they will not. That signal stops here. So let's switch that back to muscle fiber, which in turn means that pretty much this whole section up here and this whole section down here are each their own muscles, and we have a way to make our creatures move. Now, there is another way with these guys, but that is for a different type of simulation, which is not this, and we cannot switch into at the moment, but that is for in the future, and we'll talk a little bit about that after, once we actually get to those nodes. Alright, so as I said, neural tissue is the only one that doesn't actually have a physics spring, and that is because it does the same thing as a nerve, but with no spring. And that's because we might have a whole lot of neural tissue in order to interconnect the layers of an artificial neural network, and we don't necessarily need a spring for that. In fact, if we have dozens of springs when the only thing we need to do with them is connect information between two layers, you're going to bog down your simulation a little bit needlessly. So that's what a neural tissue is. Now a nerve, same thing as neural tissue but with the spring, and collectively what they do is they act as the edge of the network in a neural network. So here we have a signal, say going from our noise right here, and it will get modified by a weight that is built into the nerve or neural tissue. So it will be multiplied by that, and then that will be sent on to the node. So nerve and neural tissue propagates a signal forward, multiplied by a weight. Pretty much it. Finally, we have bone. Bone is a little special. It is not actually a spring, rather it is a relative joint. So all it does is tries to keep the relative rotation and distance between two nodes. So if we look over here, we might notice that these guys, that the bias here is spinning, and so is the noise. Now we can't see it, but the nodes attached to the bone here, they actually are not rotating at all because they are fixed in place by the bone. So that can be very useful because when you have it not connected by bone, you can actually use these nodes kind of like wheels, which is pretty fun. But with a bone, you can use them more like a foot. So you might have a creature that has a foot made of wheels and a foot that has some bone attached and some muscle propelling it forward, which is cool. And also, we will see later, useful for these guys. So I hit simulate on that real quick. Reset, editor, simulate. Yes, this game is very much in development. Let that run 200 cycles, just so we can get some movement. Up that back up. There we go. So we can see that this guy is not rotating. Now that is not because it is square, that is because it is attached to bone. Alright. So reset, editor. Let's go back here. Switch that guy back out. And there we go. So, recap. Collagen, springy. Muscle, springy. Muscle fiber, springy but can also send a signal forward. Neural tissue, not springy, propagates a signal. Nerve, springy and propagates a signal. Bone, stiff. And that's pretty much connections. So we also have select A group, select B group, connect A to B, and push layer. These are useful for when you're maybe building something kind of boxy, or especially if you're interconnecting the different layers of a network. So real quick, as an example, let's create a little 3-layer neural network here. And let's connect with the neural tissue. We'll select A group, select B group, and connect A to B. Pretty simple. Now, there's another cool thing you can do. Select A group, and then select B group. And let me just add another layer real quick. Alright. So we have A group and B group. I am going to push layer. This does the same thing as connect A to B, but then takes your B group and resets it as the A group. So now, we can just hit push layer again. And the idea would be that we can keep doing that indefinitely, which just makes making deep neural networks a lot easier. Also good if you need to, make like a 2x2 box that's long. Yeah. Alright, so we can see our B group, and then let's select A group. So that's these guys. Sorry, that's A group. Select B group, and push layer, push layer, push layer. So that's where that comes in. Alright, let's remove these guys. Yes, there is no multi-select at the moment, like rectangle select or circle select, anything like that. So we just kind of have to remove these one at a time. There we go. Okay, so that gets through our connections and the grouping options for connections. let's go through to the nodes. So, up here we can see we have a noise, 4 Hz, 2 Hz, 1 Hz, sine waves, and a positive, +1. And that's pretty much all they do. This will give you some random noise, Perla noise, that will kind of look like that, you can imagine. It will go between -1 and 1. Sine waves, they aren't actual hertz, but that's just the way that we can describe it. Just it's to say that the frequency is doubled, that's pretty much it. And then positive +1 sends out a signal of +1 through the connections. Pretty self-explanatory. Now these guys don't actually have any use at the moment, especially inside the running simulation. However, if they were in the top-down simulation, which is not like this is more of a side view where the creatures run forward, but we also are going to have another option where instead of having these levels, this is pretty much kind of like a tank or a petri dish, and it's going to have food in it, lava and rocks, that sort of thing, and the creatures will be able to sense that. And when they sense that, they will be able to sense food, something bad like lava, something normal like a wall or a rock, friends or foes. And these would have a radius, and it's pretty much almost like a sense of smell to a microscopic creature. It will just send a signal if it detects these things. Pretty straightforward, not needed for the running simulation. So let's remove those. Let's skip the activation functions, which is the third row for now, and let's go to the last 2 nodes here while we're on the subject of the top-down. This guy would actually still work inside this simulation, I just don't think it will have much use. A foot, when it receives a signal, it will increase its linear drag, which just kind of gives it some resistance in the world. As far as the top-down goes, it's almost like the creature is kind of gripping along, or putting its foot down, almost. And so that's really all that is. Now, it reacts to a positive signal, or if the signal is climbing, it will be activated, or if the signal is falling, it will be deactivated. And that's pretty much how a foot works. This guy, which you can actually see that we affixed earlier to a bone, oops. Now the reason we would do that is because we don't want these guys moving freely, we want these attached to a bone so they can maintain their relative position with the bone, which is a relative joint. Aha. So this guy is just a thruster. It will literally just propel a creature forward. That is all that does. Again, it does not really have any use in the running forward simulation. Okay, I can click that. Oh, it's not overriding it. I am not sure why that's the case. Oh, I can't get rid of this guy. Well, something's broke. Can I move it without causing an error? Can I? Well, okay. These creatures are going to look a little funny now. Oh, I can't add any nodes at all. Alright, well, I broke something. Sorry about that. And there was no warning. Error. Did I mention this was in development? Alright, so anyway. Finally, let's move on to the last set of nodes. Quick note, this is collagen. This node back here should be collagen because it doesn't pass through a signal or anything of that nature. All it does is it acts like a blank node. It just doesn't do anything except be a point for connection to connect to, and a circular collider for the world to interact with. Alright, now we have these guys. These are the pass-through nodes. So all they do is they take a signal in from a connection, like a nerve, or a muscle fiber, or some neural tissue, and they send it straight back out. Keep in mind, they will summate whatever signals come in, as do all nodes that can pass forward a signal. This guy here is a ReLU, rectified linear unit. All it does is it takes the signal in, and, well, you can actually see it. The graphs here are kind of self-explanatory. It takes a signal in. If the signal is less than 0, it outputs 0. And if the signal is greater than 0, it just outputs whatever that signal is. So pretty much it's the maximum between what your input is and 0. Pretty standard activation function in neural networks. As well, we have sigmoid and a tanh function. And I won't bother describing them. You can literally just look at the visual, the graphic on them. And that's all they do. They're regular parts of neural networks. And then here we have sign flip. This guy will just take the signal and multiply it by -1. Useful for when you're creating creatures, especially in the top-down, when they need to, for example, expand or contract their bodies or move a limb. Kind of like if the worm itself was an arm, but you need one side to be opposite than the other based on the input signal. So, for example, if this guy wanted to wave its tail, we could attach a frequency node over here, make that into a nerve, and then apply a negative signal right here. Oh, that worked. Oh, there, I can actually demonstrate. Like that. Well, I guess I can't. Whatever broke won't let me do that. But if we imagine that this bone here was a nerve, and this muscle here was a nerve, this guy here would now be able to wave its tail. We could almost demonstrate it if we were able to make a nerve right there, but we can't. But yeah, so that is what the activation functions do. Just like the activation functions of a neural network. Alright, so to recap, we got collagen and bones that can make up the body, muscles to move it, and nerves and neural tissue to send signals forward and make the brains and nervous systems, essentially. We have some bias input nodes here to get the neural network moving. Can also be used almost like kind of like an internal clock. You know how you have brainwaves? Well, these guys here can essentially be used as the starting point for a creature's brainwaves. You know, you have like your theta waves and beta and alpha, that sort of thing. Almost analogous to that. So, if I remember correctly, for example, that would be like your theta waves, this guy here, because you know it's high frequency, and well, no, those are alpha. Okay, I can't remember my brainwaves at the moment. Not the point. I'm getting off track. So we have our bias input signals. We have our world sensory signals. Again, not useful for the running simulation. The node activation functions, and then just some MISC ones over here. Alright, that's about it. Let's simulate this worm. Not too sure why that happens. Again, in dev. And yeah, something broke somewhere at some point. So, don't worry. Bugs were meant to be squashed. So before I go, let's do a quick note on what these do. In the gene pool, when these guys reproduce, they can do sexual reproduction. Essentially, all that is going to do is take, instead of taking the weight and biases from the nodes and connections in the creature and mutating them, it will take the nodes, biases and the weight, or in the connections weights, and lerp them randomly between parent A or parent B, and then mutate them. So it's just kind of a way of mixing together two brains, and that controls the percentage of sexual reproduction versus asexual. Here we have the creature count, so how many of these levels do you want to fill up? Goes up to 12. The gene pool stock amount, so the maximum is 256, so we can hold a genetic stock of 256. You can bring that all the way down to as little as 16. And the generation lifetime, which is just how many physics steps that the simulation is going to take, from 10,000 down to 200. And that's it. I hope this has helped.